Today's lesson is going to be about quantifiers. Quantifiers is going to help us update the type of logic we're using. So far we've been using something called propositional logic. And that makes sense, right? Because we've been using these things called propositions to express what we want to say. This also could be called first order logic. And so basically what we're going to do is today we're going to learn how to express things using predicate logic. And so that is also called second order logic. So basically, it'll help us express things. So previously, we've been talking about things like we'll have something like P implies Q, right? And so we have these propositions. We have the proposition P and the proposition Q. And so using predicate logic, we can actually express these things as functions. So P can be dependent on some input X. So the truth value of P could be dependent on what we're inputting to P. And similarly, the truth value to Q can be dependent on what we're inputting to Q. So we're basically now treating these like functions that just result in either true or false. So I'm going to get a little more into detail on what this means. I think it'll be easier to see with an example. So as I said, a predicate is a function that maps a possible input to either true or false. So I'm going to take the example we did last time of if it rains in the morning, I walk to campus. But now I'm going to generalize it to some day X. So I have P of X means it rained in the morning on day X. So P of X returns true only if it rained in the morning on that specific day. So I could say P of Monday is true if it rained on Monday. And similarly, Q of X is true if I walk to campus on day X. And so this can be helpful because maybe I want to be more specific about what I'm saying. Previously I was saying if it rains in the morning, then I walk. If it doesn't rain in the morning, then I walk to campus. But maybe that's not true for every day. I'm not walking to the campus on weekends, for example. So maybe I want to be more specific about what days this is actually true for. And so predicate logic helps me do that. It helps me express it, being more specific about these statements I'm making. And so I can still express what I was expressing before. So if you remember, when I was doing my propositional logic, I would express like not P. So if it doesn't rain, then I walk to campus, right? And so similarly, I can just do that with not P of X implies Q of X. And then I could, instead of X, I could put something like Monday. So both of these, that could be Monday and this could be Monday. If I was, a really chaotic person, I could make this, Wednesday. Like if it doesn't rain on Monday, then I'm gonna walk to campus on Wednesday because I have a really weird set of rules in my mind. But it just lets us kind of have more control over the inputs, essentially. So let's do a more detailed example of that. So we are going to express that statement again. So the not P of X implies Q of X. But now I want to say it only applies on Monday, Wednesdays, and Fridays. So one thing I could do is I could express it using how can I do this using what I've already learned? So one way I could do it is I could kind of join together like the statements with an and. So I could say, if it doesn't rain on Monday, then I walk to campus on Monday. And kind of like C's around that. If it doesn't rain on Wednesday, then I walk to campus on Wednesday. And then I include Friday. Here, I'll just display it on the screen a little neater. So I kind of, just kind of basically have these individual statements and then just combine them using my ands, using my logical and operator. But you can see how this can get kind of long depending on how many days you want to talk about it for. So there is a more concise way we can write it. Um, and so it's kind of similar to how you use your sum notation. So remember if you're like doing like sum of like x in 0 to 2 of x, that would be like x, oh, sorry, that would equal basically like 0 plus 1 plus 2, right? And so you could do something similar with your ands. So if I just wanted to say like and um, p, where p, or like maybe p of x, where x is whatever inputs we want to do. So like this time we had days of the week. So I could just say x is Monday and Wednesday just for this mini example. And so maybe I'll make this like do my set notation. I'll do my curly braces. So that would be like P of Monday and P of Wednesday. So I can kind of like use this and the way I use the sums. And so I can express this now using that large and. So if I let D be Monday, Wednesday, and Friday, then I can use that large and just say for all days D in my set D. So I just use D for days, right? And so I did for all little d in my set of days D, not P of little d implies Q of little d. And so now that'll be saying for Monday, Wednesday, Friday, if it's not raining in the morning, then I walk to campus. Now, there's an even easier way, I would say, to do this. And that's instead of using this kind of like those large conjunctions, you can also use something called a quantifier. And so there are two types of quantifier we're going to be learning today. The first one is called the universal quantifier, and it's also more commonly called the for all quantifier. And it's denoted with this upside down A right here. And it's just used to say something basically about all elements of a set. So we already showed this, right? That we can kind of join these statements together with a conjunction. So that for Monday, Wednesday, and Friday, if it didn't rain in the morning, then I walked to campus. And so I express that with my conjunction, but I also can say it using my quantifier. So I say for all D in D. So similarly, as I was talking about, like the little D days in the set of days. So for all little d days in the set of the days, and so remember we made D equal to Monday, Wednesday, Friday, then this statement is true. So, or you could say this statement holds. So you're not getting it confused with maybe like your Boolean true or false. So this statement holds. So if it is not raining, then I walk to campus, and it's specific to each day in D. So you're basically saying for all days in D, this is what holds. And so this is your universal quantifier. You're making a statement about all of the elements in a set. Now, the next type of quantifier we're going to talk about is the existential quantifier. So maybe I don't want to say this is true for every element of this set, but I want to say this is true for at least one element of this set. So maybe like for Monday, Wednesday, Friday, there's at least one of those days that I'm walking to campus, something like that. So for at least one day of Monday, Wednesday, and Friday, if it's not raining on day D, then I walk to campus on that day. So maybe not every day if it's not raining on day D, but I try to do it at least once a week. So I could do it similarly with my, like as I did with my conjunction, using my ors. And I could just say like, either I'm doing it on Monday or I'm doing it on Wednesday or I'm doing it on Friday. And remember, with or, multiple of these can be true. So I could do Monday and Wednesday. That'd be fine. But, only one has to be true for this statement to hold. And like my big conjunction, I can write it with my big disjunction. So I write it with my big or to say that. But I also can use my existential quantifier. So I can say that for at least one of these days, there exists a day, basically. So there exists a day D in our big set of days, big D, where if it's not raining on day D, then I walk to campus on day D. So you kind of see how the existential is kind of similar to how it kind of ties in with your or operator in logic. But basically, it just means that there's at least one instance in this set where this is happening. So now that we're talking about quantifiers, one thing you will be seeing is this idea of a free and a bounded variable. And basically what that means is if a variable is bounded, it has a specified domain. And if it doesn't have a specified domain, then it's a free variable. And so basically, like, let's say I covered up like the first part of this, and I just see f of x, y. Well, I don't really know anything about x or y right now then, right? Like I don't have any information about what is going into this function, what x and y are. They could be numbers, they could be strings, they could be fruits, like who knows? So often you want to specify a domain just to kind of say like what these elements actually are. And basically that makes it a bounded variable now because it has to be that type of thing. So for x, now I'm going to say for all x in z. And so remember, z is a set of integers. So for all integers, now I can say f of x, y. And so whatever f of x, y is, I'm saying it holds, and x is going to be definitely an integer. Don't know what y is necessarily. And that makes y a free variable because it's not defined, where x is defined and is therefore a bounded variable. And so like note that it's not like specifically defined, right? I'm not saying like x is 1, but I'm just kind of specifying the domain of what this element exists in. And so this element is in my set of integers. And so another way you could look at bounded and free variables is you could like think about it in your sums too, right? Because say in this sum, I'm summing k from 0 to 10, and then I'm just saying like k plus n. Well, now I know k is going to have the values, 0, 1, 2, 3, all the way to 10, but I don't know what n is going to be. Again, n could be a word, it could be a Boolean, it could be a number, it could be anything. So again, I don't know what n is, so n's technically a free variable where k is more clearly defined, and so it's a bounded variable. So one important thing, we did kind of show how these kind of like there exists and for all both kind of tie into logic, right? They both kind of operate similarly to ands and ors. So in other words, like there exists has a pretty like close relationship with logical ors, right? And this has a pretty close relationship with logical and. And so, unsurprisingly, we can kind of use a version of De Morgan's law with these quantifiers, where when we apply a not, when we apply a not to the quantifier, it actually flips the quantifier. So if you apply a not to for all, then it becomes there exists. If you apply a not to there exists, it becomes for all. And also notice that your negation is getting distributed to like inside of your statement. So now like this negation shows up in front of P of X. And then similarly for up here, right? So my negation applies to the for all and it comes right here. So my for all becomes there exists, and now I have a negation in front of P of X. And so we can kind of think about it like just in terms of English, like why this would make sense. So for like this first statement, right? The negation of for all of x, P of x means that P of x does not hold for all of x, right? It is not true that for all of x, P of x holds. So this is equivalent to saying there exists an x where p of x does not hold, right? Because if it doesn't hold for all x, there's at least one x where p of x does not hold. So saying this is equivalent to saying this. So again, saying it's not true that for all of x, p of x holds is the same as saying there exists an x where it is not true that p of x holds, or p of x does not hold. And similarly, you can think about our negation of our existential quantifier too. So you could say, the negation of there exists an x such that p of x holds. You could say there does not exist an x such that p of x holds. And that is equivalent to saying for all x, p of x doesn't hold, right? If there is no x where it's going to hold, that means for all of them, it does not hold. So you kind of see how these negations kind of can be distributed with your quantifiers. So just how they work to kind of like flip the behavior of each other. Another thing to think about is the ordering of your quantifiers makes a big difference. It's very important. So sometimes we'll be using quantifiers in different, like more than one quantifier. So one of the examples we had previously, right, was like f of x, y. And in our case, we bounded x, but we didn't bound y. But maybe we want to bound both. Maybe we want to say for all x and for all y, this is true. Or you could even say for all x, there exists a y. And we'll kind of like think about the logic behind like what we're really saying there. But like you might want to say things like this and use multiple quantifiers. And so it's important to note that this is not the same as saying there exists a y for all x, such that f of x, y. These are not saying the same thing. And so we'll talk more about what that means. So I'm making my predicate now called loves. And loves of xy is true if and only if person x loves person y. So this statement, I'm saying for all e and p, there exists an s and p such that loves of e and s holds. So that basically e loves person s, right? And so it's saying for all people, there exists one person such that one of the set of all people loves that specific person. So everybody loves somebody. Now, you can also say there exists an S in P, so there exists a person. So here I'm just swapping my quantifiers. There exists a person such that for all people, so this is the same again, right? Like my S and my E, like I'm using the same quantifiers, I'm just changing the order. So there exists an S in P such that for all E and P loves ES. So that this means that there exists a person such that for all people, they love that person. So now this is like there is somebody that everybody loves. Where in this first statement, it's like each person has their own person that they love. But this is saying everybody has, or there's this one person such that everybody loves them. So you can see how even though we're using the same quantifiers and we just flipped the order, we're actually changing the meaning of our statement. So finally, I want to go over some notation that you can use to kind of describe some more specific things that we want to quantify over. So one example could maybe be like, we have I and J, and they'll be between 1 and n, let's say. But maybe we also like want, so like we want to talk about like, we're talking about like maybe f of ij. So some kind of statement about I and j is true. We can make it something very simple, like I plus j equals 5. That could be f of ij. Like this could be something that is either true or false, right? And so basically, if I wanted to write this like with a quantifier, I could say there exists, and you can actually just write your I and j like within that bound. So you can say there exists an I and j between 1 and n such that I plus j. So this comma kind of just works as like a such that. Um, such that I plus j equals 5. Which is true, right? Because you can, I mean, I guess it depends on what your n is, but let's make n like, if we make this whatever, we can make this 10. Then I can pick like an I equal to 1, a j equal to 4, and sure enough, like 1 plus 4 equals 5. So that holds. So it's true that there exists an I and a j between 1 to 10. Similarly, if I wanted to maybe like be even more strict about the relationship between I and j, like maybe I want to make it so that I is less than j, I can actually write that like within here too. So like I less than j, to like be even more specific if I wanted to like add that requirement, which like you'll see for proofs, like it might be useful to kind of add that requirement. But if this is like all too much, you can always just do something like just like there exists an I and a j such that I and j are in the range 0 to n, and I is less than j. And then you can make your statement I plus j equals 5. Like that would be okay too. So it's really, like whatever you feel more comfortable expressing. But you just want to make sure you're being like as specific as possible in this like beginning definition. So sometimes like for the small examples we're going to be doing now, this isn't going to matter a ton, but when we're doing our proofs, sometimes things like this will matter. You're going to need like one big number and one small number, and they're going to need to be like within like a certain type of number, or like they're going to need to be integers. So you'll have to write like that they're in z or something like that.